Welcome back to class. We are still on electrolysis. This is lesson 2. By the end of this class, we should be able to describe the electrolysis of copper 2 tetraoxosulfate 6 using copper cathode and carbon anode, and as well as using copper as cathode and as anode. All right, let's go into it gradually. Now, electrolysis of copper 2 tetraoxosulfate 6. What are the ions involved? The ions involved are, we have 2 cations, yes, and we have 2 anions. Of course, both hydrogen and copper 2 will migrate to the cathode, but only one will be discharged. Now, which of them will be discharged? I told you those are the bottom of the series for the cationic series. So which of them comes first? Let's lazy people say can make atom 0 center. Let's hope H, copy, Cu. You see that Cu's at the bottom. So Cu, which is copper 2 ion, is the cation that will be discharged at the anode. But for the anion, oil in butter cloth, not so funny. Oil, OH in butter cloth, not still funny. Okay, still funny. You can see that OH funny. Sorry, you can see that SO42 minus occupies the 6th position, and OH is at the top. And I told you those at the top discharge for anionic series. Those at the top easily gets discharged. So it simply means that OH is going to be discharged, even though it's at low concentration. Even though it's at low concentration, it's still going to be discharged because the SO4 in question, which is at high concentration, is very far away from it's very far in the series. So, which means OH will be discharged at the end of the day. All right. Now, this is how the setup should look like using carbon anode and copper cathode. Now, what happens? Now, imagine these are particles, or these are the ions. The red we have there is copper 2 and the OH ion. Then, of course, as the setup is connected to a battery, the Cu2 plus migrates to the cathode, while the OH migrates to the anode. Of course, you know how the OH is going to be discharged. OH normally discharged as water and oxygen. Like, come back again. OH discharges as water and oxygen, while copper 2 is discharged as normal copper, which is Cu2 plus go there to gain electron, and then discharge as copper, then sticks to the body of the copper rod, which is the cathode in this case. Then, of course, OH discharges as oxygen and as water. Of course, oxygen is a gas that is to be collected over this inverted test tube. Okay, now the discharge preference. Now we said Cu2 plus is discharged at the cathode, OH minus is discharged at the anode. All right. Now, let's write the mechanism for this reaction. What are the substances involved? We have copper 2 sulfate, which ionizes as Cu2 plus and SO42 minus, and then we have water, which also ionizes as H plus and OH minus. Now, both the Cu2 plus and the OH minus migrate to the cathode, but only one is going to be discharged. Who is going to be discharged? Of course, I said it's Cu2 plus. It goes there to gain 2 electrons and is discharged as Cu, which is a normal metal. Then, and of course, discharge as Cu. All right. Now, at the anode, what migrates to the anode? I told you it's OH that migrates to the anode, and I've told you how OH normally discharge at the anode. It discharge as OH minus to form OH and 1 electron loss. That's the excess electron it was bearing. So 1 electron loss. I told you OH doesn't really exist. You don't have a compound OH, so which means it's unstable. It combines with another OH. That's 2 OH combined with each other to form water and an atomic oxygen. That's water and atomic oxygen. And I told you normally atomic oxygen does not exist. The form of oxygen that exists is O2, which is a molecular oxygen. So if you write the 2 under the oxygen, means you have to multiply every other thing in the equation by 2. So remember, by putting 2 here, it means every other thing is times 2. So we have 2 OH becomes 4 OH. We have 1 water becomes 2 water. And we have 2 E minus become 4 E minus. So that's how it becomes at the end of the day. Now, to write the overall equation, the electron in both sides must be the same, which means electron at the cathode must be equal to the electron at the electron at the cathode must be equal to electron at the anode. So since it's not equal, so use the simultaneous knowledge. So this, to make them 4, this have to be multiplied by 2, this has to be multiplied by 1. That's simultaneously we are going to be having this at the end of the day, so that we cannot cancel out the electron. Combining the equation gives birth to an overall chemical equation. This is everything at the right hand side, and of course combine the right hand side, we have 2Cu2 plus and 4OH minus, and then we have 2Cu, we have 2H2O, and that's the overall equation for everything. All right, in summary, this is the cathode, this happened at the anode, and this is overall chemical equation, just as I've explained. Electrolysis is using using copper anode and copper cathode. Now this is what it looks like. Okay, now of course, now when you use copper cathode and copper anode, remember that now you're using a rod. You're using a rod in its own solution, dipping a rod in its own solution. Yes, this is a copper. Remember that this rod is connected to the positive side of a battery, while this is the negative of a battery. Now, because you are dipping copper metal in its own solution, remember that this is a part that is not supplied by electrons. So when you dip a metal in its own solution, this is what happens to the metal. As long as the metal is not saturated by electron from a battery, coming from a battery, this is what's going to happen to the metal. The metal starts oxidizing into the solution. It starts breaking down into the solution as ion and dissolve into the solution. That's what it is. And when it dissolves into the solution as a metal ion, which is a cation, it then migrates to the cathode. It then migrates to the cathode, then when it migrates to the cathode, it gets deposited on it, then making the mass of the cathode to swell, to get bigger at the end of the day. So remember what happens here at the anode. At the anode, the copper atom breaks into the solution as copper ion, Cu2 plus. That's what it means. Okay, now let's explain this vividly. Okay, this is what happens. This is what happens. Imagine these are the particles of the copper. Actually, I told you, copper from the metal, from the anode, going to the solution. It breaks down into the solution and exists as copper ion. Remember, it means the mass of the anode will be depleting into the solution. The copper ion then migrates to the cathode. When it migrates to the cathode, because cation migrates to the cathode, when it migrates to the cathode, it goes there to accept excess electron and get deposited on the body of the cathode. Including the copper ion in the solution will do the same job as well. So at the end of the day, the copper cathode gets bigger and bigger in mass as billions of the copper ion in the solution are migrating there, and billions of the copper atom in the copper rod at the anode dissolve into the solution and migrates to the cathode. Okay, now the discharge preference. We said copper is always discharged of hydrogen. Then remember at the cathode, copper 2 ion migrates there to gain 2 electrons, but at the anode, the copper rod, which is the anode rod, is going to oxidize into the solution as copper 2 plus and leaves 2 electrons behind, 2 mole of electron behind for every 1 mole of the copper. Okay, that's what it means. All right, that's oxidation takes place at the anode, and cathode reduction takes place. So what do I mean by when you dip a metal in this solution? It breaks down or it starts oxidizing. When you dip a metal in its own solution, it creates a potential difference. For example, let's imagine that this is a metal and these are the atoms inside the metal rod. These are the metallic atoms inside the metal rod. Now imagine I'm going to dip this into a solution. I dip this into a solution. Let's say this is the metal solution. For example, gold metal in gold solution, or copper metal in copper solution. You understand what I mean? All right. By dipping it into the solution, something happens when you dip a metal in this solution. The metal begins to oxidize. The metal atom begins to oxidize into the solution. It goes into the solution, and of course it will start existing as the metal ion. even as it gets oxidized into solution, which means the metal rod gets depleted as time goes on. I come back again, the metal rod gets depleted as time goes on until the battery dies completely, or until the metal is completely depleted. All right, now then the rod after some time is depleted. That's what it means. So this is your depleted rod at the end of the day. Now this happened because some of the metal atom was oxidizing into the solution. Now let's go to the next electrolysis of brine. What is brine? Brine is aqueous sodium chloride. Brine is aqueous sodium chloride dissolved. Of course, now what are the ions involved in brine? The ions are sodium ion and chloride ion, which is in high concentration, and then hydrogen ion and the OH ion from the water. Now, who is going to be discharged at the cathode and at the anode? Now we have two cations, two different cation and two different anion. Now who is going to be discharged at the? Of course, the one at the bottom of the cation series is discharged. Now between sodium ion and hydrogen ion, who is at the bottom? Of course, calling that a series. Lazy people still can't make. Lazy people still. Okay, that's sodium. Still, that's sodium. Can't make at the same time. Let's hope minus some pressure. Let's hope there's hydrogen. Hydrogen ion is at the bottom. So hydrogen ion is discharged at the end of this. Hydrogen ion is the cation that will be discharged. Then, of course, we have two anion, chloride and OH. The oil in butter clothes, oil in butter clothes, not steel, funny. So chlorine occupies the fourth position, which occupies the higher position. Which means by position, OH should be discharged by position. But by looking at it vividly, you discover that chlorine has a higher concentration. Chlorine has a higher concentration. OH has a lower concentration. Yes, but if it's by distance, chlorine is fourth position, OH is first position. Now there's a relative closeness. Between 1 and 4, which means chlorine is too close to OH. The only factor that OH should have used to beat chlorine, which is higher than it in the series, which means it is more electropositive. Chlorine has neutralized it to an extent to tell you that chlorine is not too far away from the OH, and yet chlorine is high in concentration, which means chlorine is going to be deposited. Chlorine will be the anion that will be deposited at the anode. So you can know the reason why chloride is deposited instead of OH during the electrolysis of brine, because of its relative closeness to the series and its high concentration. Those are the factors why that will make chlorine be deposited at the end of the day. Now, discharge preferences, we've talked about why chlorine is discharged. Hydrogen is discharged at the cathode. Then, of course, now let's explain it vividly. Sodium chloride, electrolysis of brine. What is brine? Sodium chloride. Now it breaks down into Na plus and Cl minus, and then we also have water too that breaks down to H plus and OH minus. But hydrogen is discharged at the end of the day. That's because hydrogen is least in the electrolysis series and is very far away from sodium. So hydrogen gains one electron to become the normal hydrogen, but you need two electrons actually to form a molecular hydrogen, which is two electrons, and which also means you need two hydrogen ion. Then that's the Catholic reduction. Then at the anode, what happens at the anode? Chloride goes there to, of course, lose its excess electron and becomes chlorine. So remember that molecular chlorine is Cl2 and not Cl. So by putting 2 here, it means I have to multiply this equation by 2. Because times 2 and times 2. So at the end of the day, it's time to write our overall chemical equation. So which may cancel out the electrons, then combine what is left. So what is left at the left hand side is 2H plus and 2Cl minus. Then what is left at the right hand side is H2 and Cl2. That's the overall chemical equation. So in summary, this is the Catholic equation or cathodic equation, and this is the anodic equation, and this, of course, the anodic equation. This is the overall chemical equation that happens during the electrolysis of brine. All right, now I'll be introducing you to Faraday's first law of electrolysis. Faraday's first law of electrolysis states that the mass of elements deposited during electrolysis is directly proportional to the quantity of electricity that passes through it. Remember, what is it talking about? It's talking about mass, because we all agree that mass of substances are deposited at the cathode or anode or discharge during electrolysis. So the mass that is deposited depends on the quantity of what? Electricity that passes through it. Quantity of electricity that passes through it. Okay, now consider the illustration below. Now this is for this is sodium ion. Sodium ion consumes one charge. It consumes one charge. That's because it needs just one electron deficient. So this is the mass that's produced when one charge of electricity is consumed. Now, when 2 moles of sodium is deposited, it will consume 2 charges. Then, when 3 moles or 3 times 23 mass of sodium is deposited, is consume 3 charges. So it means as the charge is increasing, the mass is increasing. So that's what Faraday's first law means, that mass discharge is directly proportional to the quantity of electricity that passes through it. So that is Faraday's first law. This means the higher the quantity of electricity that passes through a substance during electrolysis, the higher the mass deposited. All right, let's talk about this. Now that is mass directly proportional. Okay, then recall that Q is equal to IT, where I represents current in ampere, T is time in seconds, M, which simply means that if Q is equal to IT and M, it means mass, which is this now, is directly proportional to IT, which stands for Q. Of course, this stands for Q. Alright, because I said mass is directly proportional to Q, and Q is what? IT. Then, it means mass is equal to ZIT, where Z is the proportionality constant. Because every proportionality sign, there must exist a proportionality constant. Okay, now mass is expressed in gram, of course. Quantity of electricity is expressed in coulomb. Then I would like us to talk about this proportionality constant, Z. Z constant or proportionality constant is also known as equivalent constant or chemical equivalence. If you are told to calculate for chemical equivalence, you need to calculate for Z. Remember, I told you that if normally that M is proportional to Q, it means M is equal to ZQ. Yes, where is the proportionality constant? Therefore, we can say Z is equal to M over Q, which means Z is the mass of a substance deposited per charge or per quantity of electricity. So, or we can also say mass is equal to ZIT, because IT stands for Q. Okay, now Z is equal to mass of substance deposited by 1 coulomb of electricity. Therefore, Z is equal to M over IT. Just like I said, Z is equal to M over Q, which means Z is equal to M over IT, where IT stands for Q. Right? Then calculating for Z for molar mass. Now, what the relationship between Z and molar mass? The relationship between Z and molar mass is that Z is equal to molar mass over EF, where E there stands for moles of electron gain or loss, and F there stands for Faraday constant. Alright, which is 96,500 per mole. Okay, remember that therefore we can say mass is equal to molar mass over EF times I times T. Yes, we can also get mass using this formula. Why am I saying this? I'm saying this because molar mass actually is mass per mole anyway. So this can give birth to this chemical equation. Alright, what are we expected to know now? What we are expected to know is that for example, we are told to determine the chemical equivalence of silver if 36 grams of silver metal was deposited at the cathode when a current of 100 ampere was made to pass its electrolyte for 5 minutes. Alright, how do we solve problems like this? Remember, we are told to solve for Remember that we are solving for chemical equivalence, and I told you that if mass deposited directly proportional to quantity of electricity, therefore mass is equals to ZQ, which means I can solve for the Z. Means Z is equal to what? M over Q. And also remember that Q is equal to IT. Therefore, you can say Z is equal to mass over IT. So, which means to get Z, I need this parameter. What? Now, we have to study our question and look at the parameter given. Parameter given are, we have mass, and we have current, and we have time. So which of the formula has these parameters? Mass, current, and time. So we use this formula Z equal to mass, and the mass there is 36 gram divided by I, and I there is current, which is 100 ampere, times T, which is time. Please, time is always in seconds. So if you are giving in minutes or hour, convert to seconds. So converting 5 minutes to seconds means 5 times 60. 5 minutes times 60 seconds. That's 5 times 60. That should give us 300. So it means I'm going to be having Z. We have 36, and the numerator here we have 100 times 5 times 60. That's gives us 30,000. So 36 divided by 30,000, what I'm having. So Z is equal to 0.0012. And what's the unit for chemical equivalence? Mass, which is the unit of mass is gram. Q, which is coulomb. So gram per coulomb is the answer, gram per coulomb. So I've just calculated for chemical equivalence. Now let's go to Faraday's second law of electrolysis. Now Faraday's second law of electrolysis states that when the same amount of current is made to pass through two different electrolytes. Now the mole, when the same amount of current is made to pass through different electrolytes, he said the mole of the element discharge is inversely proportional to the chemical equivalence. That is what is talking about. That means is inversely proportional, which means the greater the mole of element discharge, or let's put it this way, the higher the chemical equivalence, the lower the mole of the substance discharge. That's what it means. Now this simply means that the higher the ionic charge of the substance, the lower the mole of the element, or the higher the chemical equivalence, the lower the mole of the element being discharged at the end of the day when constant electricity passes through the electrolyte. Now explaining Faraday's second law of electrolysis. Consider the illustration below. This is sodium plus 1. Of course, this is 1 mole. Of course, you know that sodium consumes 1 mole of electricity, but a mole of copper consumes 2 moles of electricity, and a mole of aluminum consumes 3 moles of electricity. Of course, you know that the reason is from their charges. You will discover that this is 1 mole of these substances that are formed at the end of the day, but each of them are consuming what? They are consuming the variable moles of electricity. Now imagine, now I want to draw the relationship now finally. Now which means if you pass the same amount of electricity through all of them. Remember I told you sodium needs 1 electricity charge, a mole of copper needs 2 electricity charge, a mole of aluminum needs 3 electricity charge. But just imagine now that if I bring constant electricity, like the Faraday's second law states, it states that when the same amount of electricity passes through different electrolytes, that the mole deposited is inversely proportional to the charges. Alright, I want to make the electron stable or constant or the same amount of electricity. Now, how many sodium can consume these 6 electricity or 6 charges? It takes 6 mole of sodium to form that mole. What about another electrolyte like copper now? So that of copper, one copper needs 2 electrons, which means 3 coppers will need, which means 3 of it will need 6. So to form 3 moles of copper. Then that of aluminium, how many moles of aluminium can consume this amount of electricity? 2 moles of aluminium, because one of it consumes 3. 1 aluminium, Al3 plus, consumes 3 electrons to give us 1 aluminium. So which means 2 moles will be formed. So observe the changes in the moles. are under constant electricity, changes in moles, and with respect to their charges. It means as the charge is increasing, that's +1, +2, +3 increasing, what's happening to the mole of the substance form for different electrolytes? The mole is what? Reducing. That's 632. That's reducing. So that's inversely proportional according to the second law of Faraday's principle. All right, now from the second law, it was noted that I just talked about one electricity. One electricity means 1 mole of electricity. That it is the amount of electricity that needs to produce 1 mole of electron. So, which means 2 Faraday means 2 moles of electron. 96,500 Coulomb is 1 Faraday, and it stands for 1 mole of electron. Is the amount of electricity that produces 1 mole of electron. Then for 2 Faraday, it means 2 electrons. So, and then therefore, we can now draw a formula that relates mole and quantity of electricity. Since mole is inversely proportional to quantity of electricity, since mole is inversely proportional to chemical equivalence, and the mole of electrons here determines the chemical equivalence. All right, now if you observe inversely proportional, therefore mole is equal to Q over Fe, or we say Q is equals to NFE, where small n stand for mole, F stand for Faraday, and the E stand for mole of electron gain or loss during chemical process. Okay, now of course we know that Q is equal to IT, F is Faraday constant, and N is amount in mole, E is number of electron gain or loss. Then chemical equivalence differ for every substances depending on the charges they bear. Now, for example, the number of electron loss or gain for silver is always 1. The number of electron loss or gain for copper is always 2, because copper is always has a charge of 2. Then that of aluminium, the number of electron loss is gain is always 3. Then and the anodic, for example, chloride normally loses 1 excess electron away, but I told you that the shortest way of writing chlorine, normally chloride Cl- will normally lose 1 electron away, but because Cl doesn't exist, instead it is Cl2 that is smallest amount of chlorine, which means you have 2 here. That means number of electron loss when 1 mole of chlorine is produced is 2. So that means your E is 2 for that. Then what about for OH? We have done this one before, that it takes 4 OH minus to produce 2 mole of H2O and oxygen, and 4 electron is lost at the end of the day. So it means electron loss for this, for whenever OH is discharged, electron loss is E is 4. Okay. Now also, the mass of substances deposited can be calculated from amount in mole using the formula. If mole is always equal to mass over molar mass, therefore mass is equal to mole multiplied by molar mass, just cross multiply. Alright, where we said that is mass, mole mass and molar mass. Now, what are the uses of electrolysis? Number 1, extraction of metals and non-metals. Yes, we use electrolysis for extraction of metals from their ores. So the ore form of metals are the impure form of metal, the way they are extracted from the earth. So we use electrolysis in their extraction. Then, of course, extracting aluminium from bauxite is a perfect example. This is actually bauxite. Then another use of electrolysis is for purification of metal, e.g. something like copper. Yes, if through electrolysis. Then electroplating. Yes, where electroplating is a phenomenon or a process where a metal is coated by another metal. Yes, I will explain this vividly. Then preparation of certain important compound like sodium hydroxide, sodium transocarbonate. Alright, these are the compounds prepared. Of course, sodium hydroxide is gotten from electrolysis of brine, because Na and OH are left behind during the electrolysis of brine. I told you the electrolysis of brine, it is H that is hydrogen that is deposited at the cathode, that is discharged at the cathode, and Cl at the anode. Alright, now explaining the electroplating phenomenon. Okay, this is copper actually. Now this is a silver spoon. Now what happens to silver spoon? If silver is supposed to be electroplated using gold, it simply means that you have to dip the silver spoon inside a gold solution, and then remember I told you guys that when you dip a metal into its own solution, the metal starts oxidizing into the solution as its ion, and then this ion, which are gold ion in this case, will start migrating to the body of the cathode, then coating the body of the cathode. At the end of the day, when you as coating the body of the cathode as normal gold, at the end of the day, when you bring out the spoon out, the spoon becomes at the end of the day, the spoon becomes golden color. That's because the gold atom from the anodes and the solution have successfully coated the body of the silver spoon at the end of the day. Alright, I will see you in my next video. Thank you.